Hello, everyone. Um, Welcome to this new virtual tour of the European Southern Observatory. We are going to be your guides in this virtual experience at the European Southern Observatory, or ESO. We are going to visit today the ESO's La Silla Observatory in the next hour in the region of Coquimbo in northern Chile. So, from my side, well, my name is Farid Char. I have been a tour guide of the Paraná Observatory for more than 10 years. So, I have I am familiar with the telescopes and instruments and astronomy education. And today I am not alone. I am with producer Hector Salas. So, how are you, Hector?
Hi Farid, happy to be here again. I'm Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany. I work mostly with topics related to the circumgalactic medium, that is the environment that surrounds galaxies, and I have been a member of the team of guys for Parallel Observatory since 2019. And today I'm going to be the producer, and that means that I will be changing the videos, the pictures, but also will be reading your comments, and will give us some time during the tour for me and Farid to try to answer them as best as we can. So please send us all your questions, or your greetings, your comments, and we will address them at some point during the tour. Uh,
Okay. Thank you very much, Hector. So yeah, we're going to allocate some specific moments to answer your questions during this virtual experience. Okay, so we are going to start right now. Let's begin with European Southern Observatory. We are going to explain a little bit about the organization. So in the next screen, you will see a list of the member states. Okay. Um, so ESO is an intergovernmental organization comprising 16 member states. Its headquarters are located in Germany. Australia has also joined as a strategic partner. And Chile is the host state and home to all ESO's observatories. So since the 60s, with these objectives in mind, ESO chose one of the best places on the planet to carry out astronomy, the Atacama Desert in Chile. So at that time, Chile had started a site exploration campaign to attract international observatories such as ESO to our country. So Chile offered land, and ESO chose the area that looks best. Okay, so the mission of ESO is to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and foster cooperation in astronomy. So, in the next picture, we will take a look at the three observing sites of ESO in Chile. So, first we have the Paranal Observatory. Paranal is the home of the Very Large Telescope, or VLT. Right now, this is the most advanced visible light telescope on Earth. Now, in the future, the Paranal Observatory will also host the Extremely Large Telescope, or ELT, and this will be the largest visible light telescope on Earth. And near there will be another important facility, the CTA, and this will be an array of telescopes um, dedicated to detect gamma rays. So, and then we have Chaknantor. This is the site where the ALMA and APEX radio telescopes are located. ESO participates in those radio astronomical observatories with some international partners. And finally, we have La Silla Observatory, the site you are going to visit today. This was the first observatory built by ESO in Chile, 2,400 meters above sea level, in the region of Coquimbo. So we will go there virtually during the next hour. So let's travel now to La Silla Observatory. We are going to show you an animation. And looking at our planet, we will start this journey by land in Europe. So I have to mention that ESO is an European organization. So on this map, outlined in white, we can see the different ESO member states. So Chile is the host country and home to all ESO observatories. So to see the sites, we will travel to the Chilean mountain range. So as we move over the Atlantic Ocean, let me tell you a little bit more about ESO's mission. So to give you an idea, ESO is trying to determine what type of instruments we need to study the universe. And then is going to design the pieces to build and operate the telescopes, and is going to respond to observational requests from all the planet. And in this way, they are encouraging cooperation in astronomy. So we are almost there. We are almost arriving. You will see an amazing mountain, and you will see a mountain range with domes. Okay, and you need to take a look at the shape of this hill because maybe it will remind you of something, perhaps a horse saddle. So, in fact, the mountain itself and the observatory later were named after a saddle for horse riding. Okay, so over the years, um, ESO's La Silla Observatory has become the perfect viewpoint for studying the universe. It was chosen by the astronomical community as an observational site at the beginning of the 60s. So La Silla enjoys a large number of clear nights per year, a still and dry atmosphere, and dark skies, far away from artificial light sources. I mean, light pollution. So the observatory was inaugurated officially in 1969, and some of the telescopes are now out of service. We are going to take a look at the telescopes in this let's say drone perspective. So right now 10 telescopes are operating and 2 are operated directly by ESO. The other telescopes, several of which are robotic, belong to other institutions, and ESO will provide the facilities and support. So to get to know more information about this, we are going to approach to the main telescope of this complex, the 3.6-meter telescope at the end of the mountain. So from this perspective, you can see the different names of the telescopes, and we can see the different shapes and size, and you can see that La Silla is basically a place with a long history. So it's basically a legacy observatory, and is still able to do very important scientific discoveries and of course a very high level science. Okay, so now I am going to share the other screen. Yeah, we are going to take a look at the other screen here because we are going to talk a little bit about this beautiful telescope. And in the previous animation with the drone, we were able to see the domes here. Those domes are the other telescopes in La Silla Observatory. And if we rotate the view a little bit, you can see the general landscape of La Silla. This place is very special because from this exact place, more than 1,000 people were able to see the total solar eclipse of the 2nd of July in 2019. So this was a very special astronomical event visible from La Serena and surroundings a few years ago. And I am going to rotate the view so you can see the general landscape of from the Atacama Desert. Of course, in a regular night, in a regular day, is much more clear. The sky. In this picture, we have clouds, but it's usually very, very clear. This is the CEST. Is a former radio telescope. Now it's not in operations anymore. But most of the instruments and the technology from this telescope was moved to the Apex radio telescope, and this is a prototype. This was a prototype of the current ALMA radio telescope. So basically, the CEST, the technology or the devices from this former radio telescope is still alive, but in this case, in the Apex radio telescope in Antofagasta, in the Antofagasta region. So I am rotating the view so you can see the Andes Mountains in the horizon. So basically, we have very nice landscape here, and the main telescope of this complex is this one, the ESO 3.6 meter telescope. So we are going to access this telescope to explain a little bit more what happens here. So from this picture, you can see we are inside right now of the ESO 3.6 meter telescope. The ESO staff, the staff from La Silla, they usually call this telescope the 360 because it's 3.6 meter or 360 centimeters. So the name refers to the mirror's diameter, the main diameter. You need to remember that, in this case, back in the mid-70s, this telescope was one of the largest telescopes on Earth. Okay, so I am going to show you a little bit the dome, the main structure hosting this telescope. As you can see, it's a very big dome, and you can see here the main telescope. Currently, this telescope is hosting a very important instrument, an exoplanet hunter. The name is HARPS, and HARPS is a highly specialized instrument. This instrument is used every night to search for other planets outside our solar system. Okay, so what do you notice about the dome from the inside? Well, of course, it's huge. Okay, the altitude from the first floor to the dome is 25 meters, and all the structure of this telescope is equal to a 7-story building. So everything seems small here if you compare the surroundings with the telescope. So for example, in this picture, we have a person. Maybe you can see the person. If not, well, I can show you. I can zoom in here so you can see the person standing there. So basically, this person is just below the blue structure, and this reference helps us to distinguish the telescope itself from the rest of the structure. So now we are going to explore this structure, this telescope, in detail. So now I am going to show you a picture to the right, and you need to pay attention to 3 things here. So first, in dark blue, right here, we have the structure supporting the telescope itself. So this is the mountain, the mountain. The mountain works as a huge arm supporting the telescope and includes several systems to provide power, such as electricity. So on this arm, and parallel to the Earth rotation axis, the telescope moves to follow objects in the sky during the observation. Now, if we go there in lighter blue, we have the telescope's body, which holds the 3.6 meter or 360 centimeter main mirror and the secondary mirror. So where's the main mirror? Well, it's not visible here because it's covered by its protection system. I mean this black structure. This is a system of tabs which open and close to protect the mirror from dust or moisture when the telescope is at rest. Okay? Now, in the black tubular structure in the upper part, we have the secondary mirror, which gathers light from the main mirror in a beam. So we have to reflect this light to the instruments to analyze this light. So you will see that the main mirror has a hole in the middle, you see? So the light is sent to the instruments through this hole. So basically the primary mirror, the main mirror is concave, is curved, it's like a spoon. So when the light is going to the main mirror, when the light from the stars is going there to the main mirror, the light concentrates there, is reflected to the secondary mirror, is reflected again, and the light is passing through this hole to reach the instrument. And where's the instrument? Well, this instrument, HARPS, the exoplanet hunter, is not visible here because it's completely isolated in another room. I mean, in another floor of this building. So the 360 began operations in 1977, and from the beginning, it represented a challenge for engineering and for ESO as an organization. European astronomy was able to gather some talents from several countries to build an optical telescope in the 4-meter category, the largest and most advanced category at that time. So why was such a large telescope needed? Well, in astronomy, objects are analyzed through its light. The more light we collect, the more we can learn. In this case, a bigger mirror will capture more light, and therefore more information will be available. We will be able to see fainter objects and smaller details. Now, how do you think this giant telescope moves? Well, we have a short video to show you that. Okay, so very impressive, right? It's a big and complex machine. Okay, well, so a mirror for astronomy is not just any mirror, because its shape and surface must be perfect at the scale of fractions of thousands of millimeters. So to achieve this in the 1970s, an extremely thick mirror was manufactured, with 53 centimeters thick on average. But this also implies an extremely heavy mirror. The mirror weighs 11 tons. This is the equivalent of 2 African elephants. So if we want to build larger telescopes, we need to find other solutions. So how was the next step taken? We will see it later with the NTT. Okay, so with this explanation about the 3.6 meter telescope, now we are going outside because we need to proceed with the next telescope. But I don't know if we have some questions so far, Hector?
So far, we have received several greetings. So we have Sanjeev saying Namaste. We also have Chira Young and Bai Jin Sol are my biases, who send us greetings from Germany. They told us that they also are very close to Garching in Ingolstadt, about 85 kilometers from Garching. I have from Massimo. We also have Sway Gravin and Jose Maria and Jose Osvaldo Villarreal. All three of them usual visitors in the spiritual tours. But so far we have no questions from our audience. So let me ask me a question. What kind of maintenance is necessary to do for the telescopes, for the mirrors?
Yeah, very, very good question, because it's a usual question that we have in not only in La Silla but also in Panama. Well, when you have a telescope with a mirror like this, you need to provide some kind of maintenance, right? So, for example, the first important protection for the mirror is, I will show the picture again, is the system, right? Because this is like a cover to protect a mirror from dust, moisture. Um, in the typical maintenance for a mirror like this one, for example, in Paranal, we have a system with carbon dioxide snow. Okay, so this is usually an element that when you need to spread this element in the mirror to remove dust. Okay, so even if you have this system of tabs, maybe some dust could enter. I don't know, but with the carbon dioxide snow, you can remove all of this. This element is like a foam. Okay, um, so this is usually enough to keep the mirror usually mostly clean. But you need to do something else. You need to do something called a recoating. So the recoating basically involves to remove the surface layer of the mirror. So this mirror, for example, the surface is a very thin layer of aluminum. So you need to remove the aluminum layer and you need to put a new one. So this process is called a recoating. So essentially, when this process is finished, the mirror looks like a new mirror. Okay, so basically you are not changing the main structure of the mirror. You are just changing the reflective surface, the main the surface layer of this mirror. Okay, so this process can take a few days, and after that the mirror can restart operations again. So basically this means that the mirror in the 3.6 meter in La Silla is the same original mirror from the uh, f- f- from more than 50 years ago. So this is important because you know this mirror is very old. The telescope is very old, so we cannot just build another mirror all the time. So the recoating system is a standard technology, a standard method to keep the mirror in optimal conditions because this is the most important and delicate part of any big telescope.
Okay, thank you, Fred. And another question: can people go to the observatory in person?
Yes, that's right. People can visit La Silla and well, Paranal. I would like to also mention Paranal because basically both telescopes of this telescope in particular, La Silla and Paranal, you can visit in person. Yes. So in order to do that, anyone can book a visit in advance. So in order to do this, you need to visit the ESO website, eso.org, and you need to look for the weekend public visits program, and you can search for an available slot. In this case, you need to consider that La Silla is a little bit far away from La Serena. It's something like 2 hours and a half or something like that. So you need to book your visit, and you will reach the main entrance of the observatory, and a special bus will transport the visitors to the main mountain. So yes, you can visit La Silla Observatory on weekends. It's completely free, but you need to book your place in advance.
Okay, thank you. I think we can continue with the tour, and I would like to tell our viewers that they can send us more questions, more greetings, and we'll have another time to address them in the tour.
Okay, So thank you very much, Hector. We are going to visit now the next telescope. So the next telescope is the NTT. So the NTT is located here. Okay, the NTT is the New Technology Telescope. So the first important difference, if you compare this telescope with the 3.6 meter, is that this dome is completely different. So you need to keep in mind that both telescopes have almost the same mirror that in diameter. I mean, this one is 3.6 and this one is a very, very similar diameter, but the dome is much smaller. Okay, so the NTT was inaugurated in 1989. So I am going to enter right now to show you. It has a small and very compact octagonal dome with a system of flaps. So this represented in its days an evolutionary leap in the construction of telescopes, since it allowed hosting instruments in smaller and lighter structures with, with an improved airflow on the inside. So basically, the classical domes, such as the 3.6 meter dome, you can consider this a little bit more obsolete. Okay? So this was an improvement. So in fact, the flaps of this big dome are very special and important because the air can flow smoothly, reducing turbulence and preserving the sharpness of the pictures. So now, from the inside of the NTT, if you remember the structure of the 3.6 of the 360 telescope, the huge dome and how small our colleague seem inside. Well, in this case, this dome, is basically attached to the telescope. So if we stand in front of this telescope, we will look approximately like this size because you can see that there is a door here. Okay, so you can imagine more or less um, a person standing in front of this telescope. So the telescope mounting is also completely different. Here, the entire building spins around in 360 degrees. Okay, so when the telescope moves, is because the dome is also moving. Okay, is all the structure rotating. Now you can see from this perspective the main mirror. I am going to zoom in here. This is the main mirror. This disk is the mirror, and we can see that it reflects some light, right? So if you remember, sorry, the 53 centimeters thick mirror of the 360, well, the NTT mirror has almost the same diameter of the 360. In this case, this telescope has a 3.58 meters to be precise. But in this case, this mirror is thinner. This mirror is only 24 centimeters thick, and it's also much lighter. The weight is only 6 tons. So this is the equivalent of just one elephant. So to keep the perfect shape when the telescope is moving, we have a system of actuators. Okay, actuators or pistons below the mirror. I will show you the mirror from the other perspective. So this is the other side. So the actuators are located there below the mirror. Okay, we have 75 actuators going up and down to keep the perfect shape. So this system is computer controlled, and we call this system active optics. And this system was developed by ESO. Okay, and this technology represented a significant technological advancement, a progress, in the construction of the next generation of telescopes in the 10-meter category. So active optics has been applied to all large modern telescopes, including the Very Large Telescope, or VLT, at Paranal Observatory, and the same with the upcoming Extremely Large Telescope, or ELT, that is right now being built near Paranal. Okay, so this is the information about the telescope, as you can see here. But something important about this is, where is the staff? Where is the people working on these telescopes? So around 30 people are working in La Silla on different telescopes and tasks. The scientific and technical staff are working from the control room of La Silla Observatory, and this control room is located in another building and is actually quite far from here. So we are going to show you a short time lapse of the control room of La Silla, so you can take a look at a typical night shift. So in this picture, for example, the workstation to the left is for the NTT, the New Technology Telescope, and the workstation to the right is for the 3.6 meter telescope. And you can see that they have a lot of computers for different purposes, and you have a few people working there. So it's basically an office space, and they have to work there all night, doing the remote control of the telescope, and they can take a look at the pictures from this location. So they don't need to be inside of the telescopes at night. They can be working from that location. Okay. So this is the important information about NTT. So now I am going to invite you to take a look at something very interesting, the main scientific milestones obtained from all ESO observatories. I mean La Silla, Paranal, and Chajnantor. So please enjoy and take a look at this important video.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the main scientific milestones, but we have an extra result, something like a bonus track. We are going to show you right now. This is some news from a few years ago, but it's still important. In 2019, a team of astronomers were able to capture the first picture of a black hole. The Event Horizon Telescope, or EHT, an array of 8 ground-based telescopes distributed across the planet and coordinated by an international collaboration, achieved the first direct visual evidence of a supermassive black hole. So the picture will reveal the black hole at the center of Messier 87, a massive galaxy in the nearby Virgo galaxy cluster. So this black hole is 55 million light years from Earth and has a mass of 6.5 billion times the mass of the Sun. So I hope you like the top 10 discoveries. The discoveries achieved by ESO telescopes and the scientific staff are, of course, truly amazing. So now the tour goes on and the night falls over La Silla. So there is no moon, so we can watch the night sky, and you can see that we have a beautiful night here from the observatory, right? So now we will have the opportunity to take a look at the night sky from La Silla. So we are going to visit a few interesting objects. For example, well, by the way, this is the NTT at night from the outside. And next to the entity, from my perspective, and close to the horizon, we have this very nice constellation that is a very popular constellation, very easy to recognize, because this one is Orion. Okay, so this is the Orion constellation. Orion is the great hunter. So you can recognize this constellation because of, for example, those three stars somewhat aligned. This is representing the Orion's belt. And in Spanish, you can identify this as the Three Marys or Las Tres Marías. Okay? So in this same constellation, and next to the Three Marys, or next to the Orion's belt, we can see this. What is this? It's a nebula. It's the Great Orion's Nebula. This is basically a star-forming region in Orion. This is a very bright object. Actually, you can see this object with your naked eye. You can observe, of course, this object with binoculars or even small telescopes. Looks very, very impressive with a lot of details. So, of course, when you try to look at this picture, this object with with a big telescope, is a very impressive view. Okay, so this is part of Orion of the Orion constellation. This constellation is visible from both hemispheres, so you can see this from the southern hemisphere or the northern hemisphere. So this is the first stop of this, let's say, visit to the night sky from La Silla. So next to Orion, if we go this way, we will find a very nice star here. This is basically the brightest star in the sky. The name of this star is Sirius. Okay, Sirius belongs to a constellation called Canis Major. Canis Major is basically one of the hunting dogs of Orion. So basically, the constellation related to this bright star, the brightest star in the sky, is connected in the mythology to Orion, right here. Okay, Sirius is also visible from both hemispheres, so you can take a look at this star and Orion from any of the hemispheres, but you need to be careful because it's not visible at any time of the year. It depends on the season of the year. So if you look carefully now, and next to Orion and next to Sirius, you can see that all this area is more, let's say, is brighter because you have a more stars here. You have more concentration of stars in this area because all of this is one of the arms of the Milky Way. The Milky Way is our galaxy, and our galaxy is a huge flattened disk with a shape, with a spiral shape, but we see this as a band of light across the sky because of our viewpoint, okay? Because we are inside of this disk, okay? So our Milky Way consists of around 200 billion stars and huge clouds of interstellar gas and dust. So for example, if we explore this Milky Way arm right here, you can see a lot of dark clouds right here, but you can also see some red clouds, you see? So the red clouds are made of hydrogen, and this is the simplest and most plentiful element in the universe. So the stars basically are formed mostly from hydrogen. Now, we are going to return to the original starting point, and we are going to move now to show you two specific spots in the sky. I mean, this and this. So what is this? They are the large and small Magellanic Clouds. The Magellanic Clouds are our closest neighboring galaxies. and at the same time, they are smaller than our Milky Way. So the name Magellanic Clouds refers to the records from Ferdinand Magellan, because he was the first to make an official record of those objects during its circumnavigation of the planet in the 16th century. But at this time, in the 16th century, nobody knew exactly what a galaxy was. So, but today we know that galaxies are systems hosting tens of billions of stars, and we can classify the galaxies, um, those galaxies, I mean, we can classify them as irregular galaxies because they have an irregular shape. Okay. Now, the Magellanic Clouds are objects that you can only view. You can only see those objects from the southern hemisphere. So you cannot see the Magellanic Clouds from Europe or other places in the northern hemisphere. So many people uh, usually comes to Chile. I mean, astrophotographers or astronomy enthusiasts, because those objects are exclusive of this portion of the Earth. Okay. Okay. So something else we have from this location, some very popular object, well, actually a very popular constellation, is this one. This constellation is the Southern Cross. Southern Cross is the smallest constellation in the sky. And of course, it looks like a cross, you see. Now, this constellation is also very important because we can locate the South Celestial Pole with the help of the Southern Cross. The South Celestial Pole is basically a point in the sky. Okay, let's say another way. It's a projection of the geographical South Pole in the sky. Okay, so from the southern hemisphere, when we look at this point in the sky, I mean the projection of the geographical South Pole, we can see the stars revolving around this point. It's the same equivalent to the North Star in the northern hemisphere. So in the northern hemisphere, the observers there, they have a very bright star next to the North Celestial Pole. They have Polaris, but in the southern hemisphere, we don't have any bright star. So the only way to find this point, or let's say a nice way to find this point, is to project the longer stick of the Southern Cross 4.5 times. So this is the longer stick. So if you project this thing like 1, 2, 3, 4.5, more or less like here, you will have the South Celestial Pole. Okay, and another way to use, to find this point is to create something like a triangle using the Magellanic Clouds. Okay, so this point, the South Celestial Pole, also indicates you, if you, for example, look at the horizon. I mean, if you look at the South Celestial Pole and you look at the horizon, you are actually looking at the south cardinal point. Okay, so this is a very nice way to find cardinal points using the stars. Okay, and finally, I am going to show you that behind of the 3.6 meter telescope, we have the center of the Milky Way rising from the horizon. So this is a very spectacular view from La Silla, because the center of the Milky Way is a very bright and wide area. Okay, all of this full of clouds and dust, you see, and it's very, very impressive from the southern hemisphere, because only from this hemisphere you can see all the Milky Way in the sky. I mean, you can see all the Milky Way in winter months. I mean, winter months from the southern hemisphere. I mean, let's say May, June, July. Okay, so when you are looking at the center of the Milky Way, I mean from the southern hemisphere, you can see the center of the Milky Way all night. Okay, now this is, as I told you, exclusive from this hemisphere. So many astrophotographers, many enthusiasts of astronomy, they come to the north of Chile specifically to look at this kind of dark skies from the Atacama Desert. Okay, so now we are going to start closing this presentation. From this point, you can see the 3.6 meter telescope. You can see again the beautiful starry night, but you can see something that is not beautiful at all. You can see the light pollution here from La Serena city. So light pollution is a problem for astronomy in general, and we are trying to keep light pollution under control, because the night skies, the starry skies from the north of Chile, is part of our natural heritage. So basically, light pollution is a big problem, and fortunately, right now we have some legal regulations about that. But of course, it's very important to comply with those regulations, because this light pollution is, let's say, in the limit. So we can still observe the night sky, of course, but we hope that this light pollution will not increase. So basically, we are trying to preserve the night skies, not only in the north of Chile, but in any place with dark skies on Earth. So that's why I want to mention why light pollution is a problem for astronomy in general. Okay, so now we are going to finish, and I am going to show you the road, this little road located within the La Silla. This road is connecting all the telescopes with, well, you can see the other telescopes here. This little road is connecting the telescopes with the hotel. La Silla has a place specifically designed for the staff. We have the bedrooms, we have the restaurant, we have all the necessary things to host the employees, the astronomers, the engineers, everyone. So this will be our last stop. And you can see here that is a very nice place. This is the hotel in La Silla. This person, by the way, is the photographer who was in charge of taking all the pictures you saw during this presentation. And as you can see from this picture specifically, I am going to show you that the center of the Milky Way is visible just above you in the zenith. So this is the kind of view that is impossible to see from the northern hemisphere, because from the northern hemisphere you can see the Milky Way, but you cannot see the galaxy above you. I mean, you can see something like 70% or 75%, something like that, and a little bit lower in the sky. Okay. I mean, about the horizon. But in this place, you can see all the Milky Way all night in winter months. I mean, May, June, July. Okay. Okay. So with this last explanation, I am closing this presentation. So I don't know, Hector, if we have any other question or comment.
No, we don't have any more comments from our audience today. So if there's anything else to say, I would like to thank everybody for viewing this tour today. Remind them that we're doing these virtual tours every Saturday, switching between Spanish and English, and also between La Silla Observatory and Paranormal Observatory. So keep an eye out for when the next tour is going to be and which observatory is going to be about.
Okay, thank you very much, Hector. So, well, I would like to remind you that all those visits, information, pictures, and all the materials are available on the ESO website. And of course, next week we will have another tour. We are alternating La Silla and Paranal, Spanish and English. So stay alert to our ESO social networks. So I hope you enjoyed this tour, and on behalf of ESO, we thank you very much for joining. So see you.
Okay, we just got a last minute questions.
Uh-huh.
Let's address them quite quickly.
Yes.
So one is from Jose Maria about the orbit of the bodies in the solar system not being all elliptical, and what is like the technical name of the shape of the planetary orbits. Okay, so the more technical name or mathematical name will be a conical section. There are a couple of different ones. One of them is being an ellipsis. Most planets just follow elliptical orbit, but you also have like parabolic orbits, or things like like comets that come in and they go out, but they never come back, and things like that. So the more technical name would be like conical sections if you want to check the mathematics for that. And you have a question from Jorge. He's asking about the pollution. In Antofagasta, we have the city and also some nearby mining companies. Do they affect BLT and Parnal?
Well, not yet.
And yeah, there is the INA project.
Yeah, that's the biggest risk right now, and we hope to well, we hope that this project is moving far away from Paraná, because yeah, it's a possible risk to the observations from Paraná, because right now, I mean, from the moment when Paraná was inaugurated, the light pollution in the surroundings was very, very minimal. But from that moment until, I don't know, 5 years ago, for example, the light pollution was higher and was around the limits of, I mean, it was not an important light pollution, but yeah, was some distant light in the horizon. But yeah, with this project that you said, Hector, yeah, the risk is real, and we are at the risk of losing an important portion of the night sky. I mean, at least to affect the scientific observations. So basically, we are expecting to that the decisions taken by the authorities and those mining companies can at least respect the natural heritage and the starry skies from Paranal and other places in the Atacama Desert.
All right,
Okay.
thank you. Yeah,
Okay. So I think that's it, right?
yeah, that's it. So
Okay.
goodbye
Okay.
to
So thank you very
everybody.
much again. We hope you enjoyed this tour. And on behalf of ESO, well, we thank you very much for joining us. Okay. So see you soon. Thank you.